This particular unit covers electromagnetic theory, and today we're going to be talking about gradient, divergence, and curl. Let's look at a gradient, but before that, we already have understood from our Applied Physics 1 that there are two fundamental physical quantities, vectors and scalars. And vectors have magnitude as well as direction, and scalars have only magnitude. We've also looked at a little bit of calculus in our earlier courses, especially in mathematics course. We know about the derivatives. They tell you about the rate of change of one physical quantity with respect to the other. So when you combine these two concepts together, you get something called a branch of mathematics, or widely used in physics, called vector calculus. And a very important operator in this particular field is the gradient operator, or del. So it's also called nabla, and this is the inverted triangle symbol that is used for del. And this operator can operate on vectors and scalars in various ways. And when it acts on them, then the result would be either a vector or a scalar depending upon how it is acting on that particular function. So when we talk about gradient, gradient is the operation of del, or the nabla, or the gradient operator on a scalar point function. And as a result of this operation, what you get finally is a vector. Now, how that happens, we're going to look at that in a minute. But if you look at the mathematical definition, grad phi, or gradient of a scalar point function f, is defined as del f, okay? And this del is the nabla, the del operator, and you can see the value of that operator is given here. It's unit vector I, partial derivative with respect to x, unit vector j, partial derivative with respect to y, and unit vector k, partial derivative with respect to z. And we all know that I, j, and k are vectors in x, y, and z direction, respectively, unit vectors. So when you have this operator here, this is del operator, when you have that working on f, and what you get is a vector, and this is the direction of that vector ijk, and what you get as a result is the space rate of change of this vector f, space rate of change. So you see that all these derivatives are with respect to x, y, and z axis. So this basically gives you the space rate of change of f. So that is the basic idea behind gradient. So gradient of a scalar function yields a vector, and we're going to see in a minute how it assigns a direction to this scalar, which has, we know that, for instance, velocity is a vector, it already has a direction, but temperature is a scalar. So how would you assign direction to temperature? So if we take gradient, we can do that, and I'm going to show you that in a minute. But right now, what you can do is understand this mathematical formula for gradient and mathematical idea behind it, and let's see how it translates into physics. But before that, it's very important in vector calculus to understand which coordinate system we are working with, because certain coordinate systems are favored for certain situations. For instance, if you're talking about a line of charge, an infinite line of charge. Now, the symmetry here is essentially cylindrical, okay? So it would be really difficult to work with the Cartesian coordinate system here. So what we can do is we can switch the coordinate system to cylindrical coordinate system, okay? If we switch to that, then things become much easier because the symmetry here is cylindrical. And how you do that for grad operator is given right here. So if you want to switch the coordinate system to cylindrical, then the gradient operator, the operation of gradient, would look something like this. And let me just give you a brief idea about the cylindrical system, how that works. So if you look at your regular Cartesian axis, you have the x axis, you have the y-axis, and you have the z-axis or the z-axis here. And if you look at cylindrical coordinate system, it has three coordinates here. One is rho. So if I pick up a point here, which is, let's say, P, point P here, then I see that this point P is at a certain distance from the origin, okay? And it's making a certain angle with respect to z-axis, y-axis, and x-axis. For cylindrical coordinate system, you can define these quantities as the third coordinate z is basically the height from the origin or from the xy plane of this point, which is this height. Okay, so this value here, if let's say it's 5 units, then your z coordinate is 5 units. The height above the xy plane, so you just drop a perpendicular from that point onto the z-axis and see how far is it from the origin. That would give you the z coordinate of your cylindrical system. Now for x and y, you have to do a little bit of geometrical exercise here. You just drop a perpendicular here onto the xy plane, and then the distance of that projected point, let's call this point q. So OQ would be R. So how far your point is from the perpendicular distance of that point from the z-axis or the axis, is called R. So this coordinate is R, or rho. I'm sorry, R I've used for spherical, so I just used rho here for cylindrical coordinate system. So this coordinate would be rho. And you see that this line, the distance from this line OQ is making a certain angle with the x-axis. Let's call that angle phi or phi. So there's your third coordinate. And you got to do a little bit of geometry here, and some kind of trigonometry you can use here to arrive at this conclusion that grad phi is partial derivative of phi with respect to rho times rho hat, partial derivative of f with respect to phi, and phi hat multiplied by 1 over rho. This is not del rho, I think this is just rho. Okay, so there's a mistake here. And then partial derivative of f with respect to z coordinate and z hat. So this would be the conversion of grad phi from your rectangular coordinate system to cylindrical coordinate system. And similarly, for spherical coordinate system, you have three coordinates as r, theta, and phi again, but this is slightly different from the cylindrical coordinate system. So let me just give you a brief idea about this. So I have this rectangular Cartesian coordinate system with x-axis, y, and z-axis, and I have a point here P. And let's assume that this is a uniform sphere, okay, and this is the center or the origin of the sphere. Center of the sphere or the origin of your Cartesian system. So the distance of this point P, the radial distance, is your r coordinate, okay? And again here you see that it's making a certain angle with z-axis. You can call this theta, so that's your second coordinate. So r and theta. And for phi, you have to take the projection, you have to bring it down to the xy plane, and then drop a line from here, and then the angle between x-axis and this line OQ, let's say OQ, this angle would be your phi. So that's your conversion from Cartesian system. This is the del operator, the gradient of a function in terms of spherical polar coordinates. So the next thing is the physical significance of this gradient. How does it translate into physics? We know the mathematical definition. So if you do a little bit of vector calculus, you'll find out that what you found out as a formula for gradient actually tells you the maximum rate of change of a function with respect to the space variables. So that's the magnitude of gradient. Now, if you want to understand that, let's just assume that there are two level surfaces. One is S1, one is S2. And let's say the value of the vector is same along this complete surface. And this is surface S2. And let's assume the value of the vector here is the same along this surface. So let's just assign them some random values. Let's say that this is 4 units, okay, and this is let's say 12 units, okay. So if you look at the distance, let's say this distance is 4 units, and this distance is 2 units, okay. So you see that you can go from level surface 1 to level surface 2 along these two paths, and you can take any path. It could be this path, okay. You could take any path, okay. So if you find the rate of change along this path, you can see that, let's say this is 4 units, then delta y, which is the change in the value, is 12 minus 4, because on surface 1 it is 12 and on surface 2 it's 4, so 12 minus 4 over, if you see this is 4 units. So what you get here is 8 upon 4, which is basically 2 units. So it's 2 per 2 units of y per unit of x. That's the rate of change along this path, which is along dr. And let's say this is the shortest path and it is 2 units, then the rate here along this path would be greater, because 12 minus 4 is again 8. 8 divided by 2 is 4 units, okay. So this rate of change is higher. Along this path it's higher, and along this path is it's lower, and if you take this path it would be still lower. So as the distance becomes shorter, the rate becomes higher and higher and higher. It's like if you are climbing a mountain, if you climb a tower like this, then its distance is larger, but the rate of change of your height is quite low. But if you go along this, yeah, this is steeper. So perpendicular distance between two surfaces is the maximum. This is the shortest distance between these 2 points. So the rate is going to be maximum here. It can't be higher than this at any other path. So this is the shortest path and the rate here is maximum. So this is the upper limit. You can't have the gradient higher than the rate higher than 4. So this is only one unique direction in which the rate is maximum, and that is the perpendicular distance between the two level surfaces. So now you can call this a vector, because this was initially, remember, it was initially a scalar. There was no direction assigned to it. These are just two scalar quantities on these two surfaces, but now we have a vector because this is a unique direction. This is the only direction where the rate of change is maximum. So gradient can be defined as a vector which has a magnitude equal to the maximum rate of change. We calculated it as 4, and its direction is the direction of that change, which is along this path, which is the shortest distance between the two surfaces, or the maximum value of the rate of change of the function. So that is the physical idea behind gradient. Then I told you your del operator can work on a vector or a scalar in definite ways, and one way we just saw how it works as the gradient. Now if you take the dot product of a vector field with del, what you get is a scalar, and that quantity would be called divergence of that vector. So divergence of A is defined as the dot or scalar product of a vector operator del and the vector A. And if you look at it mathematically, then you have this vector operator del's value here, and this is the component form of vector A. And we know that I dot I would survive, but I dot J would vanish because the angle between I and J is 90 degree, and I dot J would be Ij cos theta, mod of both quantities, and cos 90 degrees is 0, so I dot J won't survive. Similarly, I dot K won't survive. So what you're going to get is the survival of I dot I, and I dot I would be mod of I, which is a unit vector, 1 dot 1 dot cos 0 degree, which is again 1. So this would be 1. So you won't have any I hat along with this. This is a dot product. So the final result of divergence of A would be partial derivative of the x component of the vector with respect to x plus the partial derivative of y component of the vector with respect to y, space variable y, and again summed it up with partial derivative of z component of the vector with respect to z. So that's the formula for divergence. And again, we have it in cylindrical coordinates as this. This is del dot A. So this is missing here. del dot A, both are vectors. This is a dot product of two vectors. This will be equal to this, and this is also divergence del dot A in spherical polar coordinates. And we know what is r, we know what is theta, and we know what is phi from the recent discussion. So this is your divergence and divergence in cylindrical and spherical polar coordinates. And that brings us to the last part of this discussion, which is curl. Okay. Okay, so before that, let's look at the physical significance of divergence. So I spot a spelling here, error here. So divergence of vector is basically how the vector field is going out from that point or coming into that point. It's the flux of the field. Okay, so flux could be outward, flux could be inwards. We know about when we talk about a positive charge and we create a volume around it, and we see that you could have, it's not necessary they should have a spherical volume. You could have a cubical volume or a cuboidal volume, and at the center of that volume you may have a charge, and then you have the flux of electric field emanating out of it. Okay, so that flux per unit volume, flux density, which is called, it's called divergence. So how much flux is coming out per unit volume, that would define the divergence at that point. So if the flux is coming out from that point, we say that the divergence is positive. And as in case of a positive charge, you see all the field lines are going radially outwards. So divergence here would definitely be positive. And we could call that we could also say that there is a source of the vector somewhere there at that point from where the divergence is positive. Similarly, if you keep a negative charge at the center of a sphere, you see all the field lines moving inwards, going inwards, and that should be negative divergence. That's called negative divergence. And what that actually means physically is that there's a sink somewhere, all the flux is going into it. And then if you have the number of field lines entering a place and exiting the place, if they are equal, field lines entering and field lines going out, if they're equal, then the divergence is zero, and such a field is called solenoidal field. Remember, in a solenoid, you have outside the solenoid the field lines exiting and inside they are entering. So the net field is zero here because it's forming a loop. So wherever there's a loop, as many field lines are entering, the flux amount of flux entering is equal to the amount of flux leaving the volume, and that's why the divergence in that particular case is negative. So sorry, zero. That's zero divergence. So the field is solenoidal. The divergence of that field at any point is zero within that volume. So that's about divergence. That brings us to the last part, which is curl. Curl of a vector field is defined as a cross product of that vector del with A. So we just had the scalar product, and this is the vector product of del with A. And if you take this cross product, you see that I cross I would be I magnitude of I with magnitude of I sine of 0, which is 0. So this term won't survive, but I cross J would be K. So that way you can cycle through all these values, and there's a simpler way of calculating this. Just find the mod of this or determinant of this particular matrix, and you should get the value of curl from this. So that's a mathematical definition of curl. You have the three unit vectors here. You have the Cartesian coordinates with the partial derivatives with respect to space, and this is the component form of the vector ax, ay, az, and you just calculate this using your regular matrix method. What you should get is curl of that vector, and here's the curl in cylindrical coordinates and also spherical polar coordinates. You have the curl here for that too. These formulas are there for your reference. And finally, if you want to look at what is the physical meaning of curl, it means that there is the rotation of field somewhere. So we know if we have this kitchen sink filled with water and we suddenly pull the plug out of the drain, you see that there's a swirl, there's a whirlpool within that. So we say that the fluid flowing through that, the velocity is, it's kind of curving around that the drain. So a similar picture can be seen here. You see the field has a rotation here. So we say that this field has some curl. Now, if you have a field like this, the lamellar field, there is no rotation in this field. Remember, a capacitor, the, the field between the parallel plates of a capacitor, it's something like this. So here the curl would be zero because the field is not, it's lamellar. So that's the physical meaning of curl. So here you would see that if you talk about fluid velocity in this case, if that is a vector, then the length of this arrow is going to tell you the magnitude and the direction also, the direction of the arrow. And you can say that if the curl is higher, that means the speed is higher here in this particular case, the velocity with which it's going out. So this could also be called the line integral, the maximum value of line integral per unit area, something like that. So if you work it out mathematically, that should be something that you should be getting. So that's the physical significance of curl. That brings to the end of this particular part of the first unit. These are the mathematical preliminaries for our electromagnetic theory. Maxwell's equations, which we are going to do at some point of time here after this, they involve these vector concepts exclusively. They have and extensively that are being used in those Maxwell's equations. So we need to have a fair idea of these mathematical terms and tools that we're going to be using later. So thank you, and I would see you in the next lecture. Thank you.